Welcome everyone. In this video we are going to prove two kinematics equations, one for displacement and another for the final velocity. Now, in one of my previous videos I already derived these equations, but in that video, which you can access from the card right now, I use calculus, and I am aware that in elementary physics, when people take their first physics class, they may not know calculus. That was the case for me, at least. So I will also want to make the proof without using calculus. I will only use algebra and graphs. So I want to prove that delta x, the displacement, is equal to the initial velocity v naught times time plus 1 over 2 acceleration, which is represented a times t squared, and final velocity is vf is equal to the initial velocity plus a times the acceleration, which gives us the change in velocity. There are two other equations, but in another video I already derived them without using calculus. I only use algebra, and they directly come from these two, so you can access that video from the cards as well. Hence, in this video I'm just going to prove these two guys. So how can we make this proof? Well, to make this proof, I want to start with the velocity formula. I will draw ourselves a coordinate system, a graph actually. So the horizontal axis will be time, and the vertical axis is going to be velocity. And let's even give the units. This is going to be seconds, and this is going to be meters per second. Now, if we are interested in the velocity time graph of an object, what we can say is it will have an initial velocity, that is that happens when time is equal to 0. So maybe we have an initial velocity like this, v naught. And we know that since, and I didn't say this, but these equations are only correct if and only if a is a constant. And of course you can put arrows here as well. These are vector quantities. Let me put them for you. So the magnitude and the direction of our acceleration is constant for these formulas to be correct. If it is not constant, then we cannot and absolutely cannot use these formulas. So this is correct for uniformly accelerated motion, where the acceleration is constant. Well, what is the acceleration? Acceleration is change in velocity over change in time. So, of course, this is just this is just an average acceleration, but we won't get into the instantaneous acceleration. That will require limit, and if we continue that idea, it requires derivatives, which I already did in one of my previous videos, so we don't need it right now. So the average acceleration, which we represent with an arrow on top of it, is going to be delta v over delta t. So this is the vector, and this bar means the average velocity. And since the acceleration is a constant for our motion, this average velocity is going to equal the instantaneous velocity at any point. This means that delta v over delta t is equal to acceleration. And how can we get delta v over delta t? Well, if you look at our graph, we can see that the slope of a vt graph is going to give us the acceleration, right? Because remember, how do we find slope? We divide delta y by delta x, and it gives us the slope m. Well, in this case, instead of y we have v, and instead of x we have t, so the slope is going to be the acceleration. And of course I should graph this graph. Let me sketch it. Maybe it looks something like this. And so as I just argued, this is going to be the acceleration. Let me call it perhaps like this. The slope here is going to give us the acceleration. Alright, well then how can we write this formula using this idea? It is simply going to be, if this is v of t, we will represent it in the slope-intercept form, which is, I'm writing the general math formula, it is y is equal to mx plus b, m is the slope, b is the y-intercept, x is the independent, and y is the dependent variable. So in this case we will have v of t is equal to, our m is, as I argued, it is the acceleration, and let's put the arrows as well. It is the acceleration. Also, we should put the arrows here. Excuse me for getting that. we have the acceleration, then we have x, which is the independent variable. And the independent variable in this case is just time, the t, plus b. It is the y-intercept, so it is going to be v naught in our case. V naught. And of course, if we rearrange this and if we call the velocity at time t the final velocity, we get that vf, the final velocity, is equal to the initial velocity plus the change in velocity, which is the acceleration times time. So we proved one of our equations. Now let's prove the other one. And to prove the other one, I will actually use the same graph again. But this time I won't consider the slope of it. I will consider the area bounded between the graph and the horizontal time axis. So I am interested in finding this area. Well, actually, let me draw it on a new page so that we have enough space. So we have the same set of axes again, time in terms of second and velocity in meters per second. And we again have a v naught, an initial velocity. If we draw our graph, it is going to be a line because the acceleration is constant. Now, if I want to find the acceleration at this point, at time t, what I will do is I will draw a dashed line like this, and I claim that this area bounded with the line and the horizontal axis, this is going to give us delta x. And how can that be possible? Well, this is going to be correct because if you multiply velocity values with time values, you get a distance. Okay? And since we do it with changing velocities over some time interval, we will get the actual delta x. And if you don't think this is correct, well, you can convince yourself by actually multiplying the units of our graph. We have meters per second and we have second. If we multiply the units of the axes, we get meters, which is a unit of position. I mean, what could it represent? Could it represent the position itself? No, because this is independent of our starting position. We do not get information about our initial position from this graph. We would need a position versus time graph to be able to get that. But we get information about delta x, the change in position. Okay, and if we know the initial position, we then can figure out the final position as well by adding delta x and the initial position. So how can we figure out what delta x is? As I said, delta x is going to be the area bounded by our line and the horizontal axis, the time axis in this case. So I will break it down to two parts. We're going to have this rectangle, and the area of a rectangle is simply width times length, so it is going to be v naught times time. And then we're going to have this part, maybe let's do it with this color. This is going to be the orange. So the orange is going to be, if I call this v final, then the difference here is going to be delta v. Of course, right? Vf minus v naught gives you delta v. Final minus initial is the change. So we get that delta v times time is going to give us the area, right? No, we also need to divide by 1 over 2. That is the formula for finding the area of a triangle. Height times the base divided by 2. This is important, please don't forget. And we can substitute for delta v. Delta v is going to be equal to the acceleration times time. Right, we just discussed it here. I multiply both sides by delta time, and since we start at time is equal to 0, instead of delta t, we can just write time. So that's why I write t here, to make it short. So as I said, delta v is equal to a times t. And if we substitute that here, for the orange area, we get 1 over 2. Instead of delta v, we're going to have a times t. We have another t, so t squared. And now, if we add both areas, the area of the triangle and the rectangle, we're going to have v naught times time plus 1 over 2 a t squared. And just like that, we proved the other formula. And using these two, you can derive two other formulas, one for average velocity and one the so-called time independent uniform accelerated motion formula. And as I said, I derived them in one of my previous videos without using calculus, so you can find it. And if you know calculus, you can also watch the formal definition with calculus of these two formulas. Anyways, I hope this was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.